Okay, my friends, prepare for this. There are huge new discoveries on neutrinos. Now, I've been hammering away about these neutrinos for years, but in the last few months I really focused in, and I think they're paying attention to a degree, because of a major discovery about neutrinos. But also, basically, what are they? This is Anton Petrov, and he's a nice guy, and I am going to talk about what he says this great new discovery is, and let's see if it works out with my information, because I have as much information as anybody on this. That's right. Start with that, because that's how it's just true. And I can show you my information because I'm using CMOS, right, to actually watch these things happen. And I'll show you how CMOS works and why it can see electron neutrinos and muon neutrinos. How does that work? How can you see down that small? I'm going to explain to you how CMOS, which is complementary metal oxide silicates, receives these different frequencies, which are energy levels, and then it has its own amplifier built into every single pixel. So that's why I say, oh, you can't see that, you can't see that. Yeah, absolutely I can see it. And it doesn't get damaged because we're just using light. We're not using what CERN and Fermilab do. They smash these particles here together like this. In other words, they hit a ball, they got a ball like that's a proton, but they hit two of them together. All they're doing is hitting two balls like that together, and then they get splashes of all this stuff. Way too much. We use light. We're down here. So we don't have any damage effect. When they smash these together, it's like hitting two dump trucks together, and boom. And just everything goes everywhere, and it destroys the CMOS. That was the different discussion I had with University of Geneva when I went there for particle physics. I said, yeah, we could see it. We could see it with the CMOS. And they said, no, you'll destroy the CMOS. And I said, no, you destroy the CMOS because you use these. You're using this big bomber. We're using light. We're down here. CMOS is designed for light. We'll get into it. Okay, my friends, this goes back quite a number of years, and this is dipole electron flood model replaces the standard model, and this is on academia.edu. They got me all over the place here for the electron flood theory, and I'm the one that proposed it, and I can show you the evidence to support it. And this just says this was back from well, this is 7/20/22, but I had that in 2019. I wrote the paper that this book is based on, and this is really not much of a book based on my theory. This is more of it's a coffee table book, but this view of my mentions. Oh, right there, 6,296 papers mention my name. That's a lot. In the academic realm, that is a ton. They just don't want to talk to me because there's nothing they can say about what I'm doing. But it's all over this academia.edu, and it's all over this internet stuff now. People understand it. Everybody's talking about it. And in the last few months, it's just been a very hot topic. All right, it's just incredible. They are really going hard at this AI-detected anomaly may uncover novel physics beyond the standard model. This just popped up on my screen a minute ago as I'm watching this video I'm trying to make about neutrinos. Everybody's understanding. They don't know how gravity works. They don't know how dark matter. They don't even know what the universe is made of. They say, well, everything's made out of dark matter, but we don't know what dark matter is. Well, I can show you all of these things. It's very, very simple. But you have to be able to step back and watch the evidence, not just dismiss it because that's impossible, that's impossible. That's all I've ever heard. That's all I've ever heard. But when I show them his possibilities, they say, well, yeah, okay, have a nice day, see you later. That's not how I do physics. That's not how I do anything. I look at it, I think about it, then I try to make other people respond. You can't get responses. All right, this is not a new theory for me. This goes back to 1970, right after I got out of the Army. And I got deep, deep, deep. As deep as anybody, because it was just starting at that time. And my conclusion was that the transfer of energy, all energy, is from light to atomic vapor. What is atomic vapor? It's the neutrinos. And there's only two types of energy. There's dipole-dipole interactions, and then there's induced dipoles. But that's the only types of actions you have. Two types of dipoles. Well, and I mean, I got real deep into this, and you couldn't get any deeper. There was no deeper to go. I had all, and I found out nothing was working right, and I confronted the professor about it. And he said, no, you just got to say what I tell you to say, and you'll be okay. I said, no, I'm not going to do that, and I'm going to and I'm not, and I want an A. I said, I'm not kidding you. This happened. I'm not kidding you. This is true. I said, I want an A, and he says, I've never given anybody an A. I said, you're going to give me an A. And he said, why should I give you an A? I said, because I'm going to challenge you to doing a dipole molecular moment of some polar molecules, which were really sophisticated molecules, and we had to find out the centers of magnetic interaction based on their angular build and all kinds of stuff. And I laid it out in front of him. He says, all right, I'll give you the A. Now, I've been really hitting this stuff hard for a while. Dipole electron flood theory explains gravity, dark matter, Brownian motion, subatomic particles, quantum gravity seen for the first time on subatomic level as dipole interactions. This is a couple of months ago, a month ago. Neutrinos may be more common than thought and easy to create. Yes, they are. Those are neutrinos right there. And I always kept hammering on about this. And here's another one, just in universe of fractals. And nobody knows what they make. Nobody knows anything about the particles that exist, that we live, or even part of us. We're made out of these same particles. It depends on how they're globbed together. Like that's going to be a potassium. You take a bunch of these off, it's going to be a carbon. It doesn't matter. It's the way, they're like snowballs. It's a very strange concept, I have to admit. But there is zones of stability. And that's all these are, zones of stability. Right? Phosphorus, silicon, aluminum. And all it is less and less particles. And then they get stable at a certain point. And then there's a few thousand more particles between the next zone of stability. That's the key. This one here is not one, which they call it. That's 1,825 or so. This helium is not like 4 particles, which they claim. It's like 7,000, I forget what it is. But every single proton is multiplied by 1,823, and neutrons are 1,824. So how many they say are those in these, just multiply them those numbers. So you're thousands and thousands of times more particles to deal with, but that gives you the elegance of life. Because that's what life is made out of. So we can do all kinds of things. But anyway, now they get AI-detected anomaly may uncover novel physics beyond the standard model. Well, let's look into some novel physics. You see, everybody's trying to put their spin on this. This is basically the same particles I'm showing right here in the book. All it is a dipole. One of them has the energy and one of them has the carrier, the mass. I'm going to show you all this stuff in so much detail it can't be denied. All right, check this out. I've been showing that light contains dark matter. Half of light is the dark matter. And so now they say scientists propose a new way to search for dark matter. This just came out, I don't know, a couple days ago. And here's what they say. Most dark matter experiments hunt for galactic, all the way everywhere, which rockets into Earth directly from space, which is the dark matter. Yes, I agree with that. But another kind might have been hanging around Earth for years, because everything consists of partially dark matter. They're right. And it says dark matter goes into the Earth. Dark matter's in the Earth. It's in us. We are made of dark matter, literally. That's the mass of us. All the light part, there's no matter to it. There's no mass to it. And they know this. This is not unknown. There is no mass to an electron neutrino that they can determine, and I have to agree with that. And I can show you why in an atomic bomb blast. That's the energetic particle. It burns. Then comes the black particle, which smashes everything down. So the dark matter and the white matter comes down as heat, but the dark matter with it goes into the Earth, and the Earth is literally growing. Anytime dark matter hits something, incorporates into it, it's another particle. It's getting bigger. I don't know if I showed you this or not. This came out also. New particle, yes or no? AI detected anomaly may uncover novel physics beyond the standard model. Well, yes, and it has. And they're using exactly the same technique we use. You see this right here? They're coming in this way with a focus of electrons. They're forcing it to pinch through a venturi. It comes out the same way that it went in. You just don't realize it. And it took me a long time to come up to the realization. It starts a certain way and it ends a certain way. And in the middle, you have just unimaginable amounts of energy. So if you can get between this and coming back to what it was here, you're going to be able to use that energy. All right. So anyway, remember, that's the venturi, and they're spraying out. Wow. This is amazing. Listen to this. I think they're using protons coming in here. We're using light. And light has its own field built around it. And when you crush those fields together, that's when you get energy. Field against field creates energy. It's called a Kashmir effect. And I think they're using big bombers that coming in like this. And so I don't really know what their result is, but we're using this. Tons of these coming in, just little ones. And when they gang all together here at the venturi, only the white part can squirt through. All the black ones go flying backwards. And again, I will show you this. So this just blows my mind. This is basically what we've been doing right along, that exact sort of setup. And here it says discoveries and future research. They call that a neural network. Why, I don't know. It says it didn't find anything glaring for new physics in the data set, but it did spot one anomaly scientists think is worth further studying. Listen to this carefully. An exotic particle decay. An exotic particle decay. All of a sudden they started falling apart at an energy of around 4.8 tetra electron volts. Results in a muon, okay, the muon is the black particle, which is a type of fundamental particle. The muon is the fundamental, tiniest black particle, and a jet, which is an electron shower of other particles that does not fit with the neural network's understanding of standard model interactions. But no, because these are nothing but little bit bar magnets, and they break apart. Everything they say proves everything I say. All right, stick with me on this. What we're looking for is neutrinos. Well, what is a neutrino? Well, there's two different types. There's a muon neutrino, and then there's an electron neutrino. All right, and this is what happens to them when they are accelerated, and then they hit heavy water, or water of some sort, some medium that will, impact them and slow them down. And what you end up seeing is the muon neutrino ends up showing as a muon, which is a black ball, and it's fixed size, fixed, it does not change. And then you have the electron, which is a fluffy white thing. It depends how big it gets or small. It depends on how much crushing you're doing. And then it comes out as showers. All right, and so these are neutrinos. So what we're looking for is neutrinos. Well, we found them. Okay, stick with me. Let's work this thing backwards. This is where the neutrinos separate. Remember I said you could end up with a muon, which is a black ball, never changes size, it's one fixed size, and then you get this white fluffy shower, which is from the electron neutrino. Two different neutrinos. One is black, one's white. They're just like locked together, just like this. They're supposed to be like that all the time. When they break apart, that's when you get all this hell of a lot of energy. And then they come right back together. They start a certain way, they come back together a certain way. This is actually fission. That's when the black breaks apart from the white. It's fission. When it comes back together, it's fusion. And that's exactly what happened here. This is a subatomic nuclear, because they're nuclear particles, explosion. That's what it is. It's a nuke on the desktop. Now this couldn't be any more clear. This is the point particles that they found at Fermilab. And this one here has no weight whatsoever and all burn. And this one has no burn and all the weight. And has a fuzzy edge around. I'm going to show you the article in a second. It's called point particles. Now, half this one together here would be what we would call an electron. So you need a carrier to carry this. It has no mass. There's no. It doesn't go. There's no weight. But it burns like hell. This is the carrier. They always said there was a boson carrier that carried the neutrino. Now, but they call them both neutrinos. It's a little confusing. And two of them back to back, which are two bar magnets back to back, make this a photon. The white one gets small and big, so it can squirt through the little venturi that we have. The black one stays the same size. You can't get through. So these two are incorporated into light. If you only had a half a set, that's basically an electron. That's going to burn into you. It's going to cook into you as heat. Light sort of bounces off because it's got a field surrounding the whole thing. If you only had half of this, you'd have it would want to incorporate into you as part of your mass, or as to be heat, which would come and go. That's what electrons do. They come and go, like a chameleon. All right, this is the point part. This is the concept of point particles. Now, what are point particles? This is from Fermilab. They are right there. It's the exact same particles I just showed you a second ago. And they say exactly what I say. This one has no weight whatsoever. That one has all the weight and it's a fixed particle. In summary, the extended particles have a fixed size. That's the black one. It's fixed. It never can change. They may have a fuzzy edge around them. Yes, they do. It's the color of the intensity. The point-like particles are mathematical extractions, zero size. That's the glowy one. But even zero-size particles have extended effect due to the field. Now, that's still a little confusing to me, but he's right. These two are together as an electron, and back to back is a photon. And this one has no weight and no mass to it, but it has all the burn, and this one has all the weight and mass and no burn. And I can show you that. I'm going to show it to you right now in an atomic bomb blast. It proves exactly what I'm saying. All right, this is going to prove exactly what I am saying about light and the dipole electron flood theory. Let me just bring this up real quick so you understand. Where'd you go, dipole flood theory? All right, what you're going to see, these glowy ones, the blue, the green, and the red, those are the energy ones, and they just burn. They have no mass, they just burn, and they're the ones that are going to go first. And then the black ones are going to be the pushers. They are the ones that push the glowy ones. And the glowy ones come out first, and the house is just going to smoke. And then the black ones are going to hit it, and it's just going to go flying. That's what dipole electron flood is all about. There's a separation of powers. When that thing goes off, all the white ones go off first. Then the black ones trail. And here it comes. Okay, keep your eye on this. They just got it all set up now. And now the truck's gone and everything. Here it goes. I'm going to stop here and there. The bomb has gone off. And what do you see? I'm stopping it. It's still just irradiated. It's just smoking. There's nothing moving. The telephone poles are smoking. The wires are smoking. The house is smoking. The shingles. Everything is facing the light. Now, they have a hardened camera here facing away so they can watch all this happen. And then now this is happening pretty fast, because I've got it real slow. But watch, it's obviously 100%, no question whatsoever, there's a separation of powers here. And these have no mass. Mass means it's going to push it. It's not pushing it. Watch. It's just smoking. It's just smoking up like it was. Look, now watch. I just stopped it because now is the heavy-duty particles right in the mix right there. That was just fortunate. It stopped like that. This is right in the mix of the hot and the cold particles slamming. And now the house is going to take off. Look at that. Isn't that stunning? Boom, there it goes. Boom, 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 boom. That's because of those dark particles. The white ones just burn. They don't do anything. They don't move anything. It's just exactly like they said at Fermilab. They're theoretical, but they do have that field. And the field is the energy. I'll show you why I can prove that too. Okay, follow me up on this. I always talk about the venturi. Venturi. Well, what does it look like? I'm going to show you right now. This is where the venturi is. You can't see it because when you create this kind of energy, it's like looking into the sun and you just can't see anything. You're just blinded. But here's what it looks like. These here were the particles, the black and white particles together. Now let's look at that first of all so you understand the particles that are coming into that system here. Let me just turn this off. Well, I'll leave it on. Now, you see what's happening here? The light is coming this way. Now we're all the way up to the photon phase. The photon phase doesn't happen until it gets ready to explode. You see, this is the explosion. And the reason it shows as a photon, it's reacting exactly like it hit a wall and bouncing back, because the bounce back from here is so intense that it's slapping it back. And that's why it shows up as an actual photon right in the middle of the air. That's just not normal. They don't show up like that. They show up like these neutrinos, and they don't show up at all. They're all over in here. There's a ton of them out here. Dust here and there. And then they show up as neutrinos, which are these little jobbers here, which aren't fully photons. And then they have a different phase to them, which is this phase, which aren't photons yet either. But these are full photons. Now, let's look at it a little deeper. All right, I just showed you the photons coming out of the laser heading this way, and then they explode at the venturi. Well, this is what you're really looking at, and this is what a venturi is. This is the laser, pulsed red laser, and they come out in these little photons. They're not coming out all busted up in little bit of pieces. They're coming out as these neutrino arrays and photons. Now, at the venturi, whole different story. And why is that, Roger? Well, the venturi is a restriction. All right? It's an extreme restriction. And we have two pins. You see a pin like this, a pin like that, and the light is going between those two pins. And as it hits that curvature here, it has to crush together. This is just as good as hitting head on. CERN and Fermilab hit head on. We're hitting sideways. It's the same thing. No difference whatsoever. Except we could force them to hit. They can't. When they're trying to hit them head on, they come like this and they go boom, because they hit the magnetic fields. They only get like 25 reactions for every 100 billion particles, something like that. It's ridiculous. We get almost 100% reaction because they're coming together, and when they hit here, they have no place to go. So what happens is the white can shrink down and end up squirting out. The black can't do that. So the black bounces back, and it's just going to slap, 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 squirt, 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 squirt. Now, all around the edges, the black wants to be so desperately reattached that it just, and there's all kinds of extra black laying around. It appears to me there's just a ton of dark matter that's just laying around there that's ready to be incorporated into a particle of light. And then when this happens, they turn right back to what they were before. So you started with this, you ended with this. In the middle, we just separated them. And I have a design that if you can get in between here before they get back to the dark matter and let that seek ground by itself, you could use all that energy. I mean, tons and tons and tons and tons. Electron showers, that's the cat's meow. You get electron showers, you're way, way up there in energy. That's what they're trying to do right now, is electron showers. And we did it. They're right there. Those are electron showers. That's what it was. There's muon neutrino, electron neutrino attached together like that. And when they hit the venturi, the black is smacked away, and then it tries to incorporate back in. The white is on its own right here. It's just 100% white. That's raw energy. And that's that thing that they found in their experiments. This anomaly showed up at a certain energy level. And that's the energy level created by the venturi, which creates Casimir effect. It is extreme compression of frequencies. It's just like hitting two head on. All they're doing is compressing the waves. We're compressing them by going this way and not letting them get away. They come together and they just have nowhere to go. So the white one squirts through. And don't forget, these are the same particles. These are identical to what they see at Fermilab and CERN. And see how small that one is and how big this one is? These can get down to almost nothing, and they squirt right through that venturi. Zip. And the black ones can't. They're just too big. They're just like a bowling ball, can't get through there. And they bounce out. But the white comes out splashed. So this is what we started with, and this is what I end up with. And they come through with they look like Higgs fields. I'll show you in a second. All right, this tells the tale pretty good. This is the pulsed red laser. Boom, 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 boom. All of these little particles that are lit up are gases in the air. They still have electron fields around them too. So they're going pump, 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 and they're puffing up. Now, what is this right here? This is the acceleration phase. All right, so here's before it's well, it's actually starting to accelerate. That's the only reason you see the wave. You wouldn't even see it. It wouldn't light any of this stuff up. It's pushing so hard against everybody else's field that there's a glow. That's the only reason. Like up here, you don't see any. There's a ton of particles up in here, and you know that because you're seeing them way out here. They're finally concussing with enough vengeance because this is bouncing back. You see how brilliant these tips are? You have all those same fields back here. They come through here just the way this was. Only this one here is headed for the venturi, so it has to accelerate. That's why that one's glowing. These didn't accelerate because they're not in the venturi. So they just came through here, but now the pushback of the explosion is what's making their field glow. It's a difference in the push to shove. These all of a sudden hit that wall. And this is literally a wall exploding out from that explosion, where all those particles are separating. The black and whites are separating. They have to go somewhere. When they do, it's just an enormous amount of increased energy. And that's the only reason you see these. No other reason whatsoever. They just keep on going. Nobody ever know they were there. And the same thing with that one, except that it's accelerating. Now, so what do we see right here? This basically looks like a Higgs field. And so does that. And so do these. This is after they come out. They're coming out here. There's nothing but white. I could show you a lot. I have so much stuff on this. It's just staggering. And again, this is Rod Warren, and I thank God for Rod doing all that work. And he's an amazing guy. I'm just going to leave it at that. I don't know if he wants to be associated anymore or not, but I want him to have credit for this, because I would have never, ever, 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 ever times a million known about this. Except, well, I knew about the theory, but I couldn't prove it. How are you going to prove the theory? You can't see this. You can't prove it. Well, you can see it now, and it is proven. And I know that they're looking, because I'm seeing articles come over every day. Knew this, knew that, and they're putting a little twist. Everybody does that. They want to nibble into it, but on their own little terms, so that they're, not just repeating somebody else. I understand that. That's what the discovery is all about. They got an idea. Put it out there. Let's take a look. Now, this is light slowing down. You see that? That's coming fast. Slowing down. Light speeds up, slows down. That's all nonsense. We've been working with the ridiculous physics, and they say these are laws. That's a law. Oh, no, that can't happen, because you're breaking Einstein's 100th perfect law. No, you're not. You're just understanding what's going on. Light isn't being stretched and pulled away from Earth. It's slowing down. It's just being emitted from wherever it's being emitted from. That's all. It's slowing down. So it shifts to the red. There's no genius going on here. I'm going to tell you that right now. It's just, it's obvious, so obvious. It's just incredible. All right, I just got to make this so clear that you can't possibly miss it. This right here is a photon of light. Well, this is what they would consider a proton, but they think it's just one big mass that you can fracture apart, but that's just not true. It's just like a snowball of 1,823 particles, just like that. It's called a Dirac neutrino. It's both sides of the neutrino. Now, for us, it's this. It's just that. This is just a little bar magnet. That's all it is. And if you took two of them side by side, that's light. That's light right there. And one side glows, and the other side is the carrier. This has all the weight. So anyway, this is what they got to understand. The base part, which is the neutrinos. And now they are. Everybody's screaming about neutrinos. All right, this is absolutely, totally simple. This is a proton. That's a neutron. A proton has 1,823 particles, and a neutron is the neutral because it's even, 1,824. Now they're slamming them together. And when they do, they get all these particles. It's a zoo. Just a bunch of particles. Well, what do we see? We see our photons. They're seeing them too. They just don't realize what they're seeing. These are the photons. And they are down in this range right there. Little bitty bits. These are the ones they are slamming. So what do they end up with? They end up with chunks like this, and chunks like that, and chunks like this, and chunks like that. They just got a zoo of particles. And they think they're all different particles. No, they're not. They're all from the same two particles, which was that black and the white one. And they see them coming off as the photons, but it's just in such a mix that they get lost. All right, I think I showed you this maybe, but if not, here it is. This is about the new particle they say they just discovered. This was the big story about this gigantic new discovery. And all they're using is the same technique we were using. Well, I think they're using protons, which is going to just still give them a mass of particles just that are going to be globs of this and that. Unless somehow they got it tuned so perfectly. Ours was tuned. And again, Rodney Warren. Thank God for Rodney. So I don't know what they think. They got the collaboration involves scientists, 172 research organizations. Okay, my friends, this is Anton Petrov. Nice guy, and he's a science communicator. He speaks about scientific topics that are really at the top, and he's had major discoveries about neutrinos. I haven't watched this yet. I only got up to like a couple of minutes, and then I said, ooh, I'm going to have to show this. And I hope Anton's okay with that. I've never had any correspondence back from him. I've tried to correspond to him. If you know Anton, to have him, if he would, engage with me. I'd love to talk to him or show him what my evidence is, because he's showing all the evidence from mainstream. You know, they eliminate the unwanted. And I am unwanted. There's not too many people that want me, I can guarantee you that. Okay, once again, this is Anton Petrov. Nice guy, very engaging. He's not like me. I think he's a little more generous than I am. But anyway, here's what he has to say. And you know, he's easy to listen to, and he's pretty well informed about what he's presented with. Now, I got a feeling he's been watching my stuff, but I don't know. I have no idea. Nobody communicates with me. Here goes.
Now we have something really exciting in regards to neutrinos. An exciting report coming out of IceCube neutrino detector, an enormous detector that's currently in Antarctica. But before we talk about the detection and what exactly it means, I actually wanted to briefly start with neutrinos in general, just to help you understand why this is kind of important. And that's because one day, there's actually a really big chance that neutrinos, the mysterious, barely understood particles, may actually be able to explain so many different mysteries of the universe that we currently cannot explain. And that of course includes things like dark matter, but also the idea of Big Bang and what happened in the first second after the formation of the universe. And so, hello wonderful person, this is Anton. Let's discuss some of these recent, exciting discoveries in regards to neutrinos once again. But first, okay, but what are they? What exactly is a neutrino? I mean, most of you are probably familiar with protons and neutrons inside various atoms, and of course electrons surrounding them. But
see, that's the mainstream take on this, that there's neutrons and protons in the core, and then there's all the electrons surrounding it. It's not exactly that way. And they don't know how many electrons. Let me go back to that, because this is where it gets a little confusing. They're sort of in the right mode and off the right mode. Neutrons and protons are not just these balls, they are these. Each one of these has a certain number of particles. That's what makes up a proton. It's stable at that number. And then the next zone of stability is like another proton's worth up, another neutron's worth up. But there's thousands of particles between zones of stability, which we call atoms. All right, and then you have all the isotopes in between. And isotopes are just like, this is supposed to be a carbon, but there's a couple of them missing. It's still a carbon. And then even there's some more missing. It's still a carbon. And there might even be a bunch extras, but it's still a carbon, because there's so much variety between each zone of stability. This was never understood before, I don't think. But anyway, it's sort of what he's talking about, but not. Let's listen to it, because I'll try to explain as much as I can. This is going to take a little time. I was going to try to do everything in 10-minute clips. It just doesn't work.
familiar with protons and neutrons inside various atoms, and of course electrons surrounding them. But despite similarities in the name, neutrinos have nothing to do with neutrons and are actually super weird in comparison. And they're actually only named neutrinos because they're so tiny in terms of mass and because they're neutral, just like neutrons. They don't have any electrical charge.
See, that's not correct.
You understand? This is kind of important.
It is kind of important, because that's not right. All right, listen to what he has to say, because this is not going to be correct.
Actually super weird in comparison. And they're actually only named neutrinos because they're so tiny in terms of mass and because they're neutral, just like neutrons. They don't have any electrical charge. But unlike a lot of other particles, including protons and neutrons, they don't actually interact with anything except for just a little bit of gravitational force and the weak force. And so as a result, they generally go through most matter without touching or interacting with anything. It's extremely difficult to detect them, which is why building an enormous neutrino detector is really the only way to even see them. For example, here's the overall size of the IceCube neutrino detector. It is absolutely enormous, but it's only able to detect 1 or 2 neutrinos once in a while, simply because their mass is so low, so gravitationally they don't really interact with pretty much anything.
That's just totally wrong, but we'll go along with it.
Also have no charge, so no electromagnetic interaction.
Totally wrong.
And most importantly, they don't interact with anything through strong force. But
totally wrong.
But what's even stranger, ever since you began watching this video, roughly around 8 trillion neutrinos pass through your whole body without really doing anything, without
totally wrong.
You feeling them, without them interacting with your body. And basically the only way we even know they pass through you is through various experiments we're going to be discussing very soon. And so in essence, neutrinos are believed to be some of the most common subatomic particles in the entire universe.
They're the only particles that exist. But there's 2 of them. There's a muon, an electron, neutrino. That's all. And everything is made, is made from those. This is why all of these assumptions are based on standard model assumptions, which are wrong, just totally wrong. All right, let's just make sure you understand where we're at. We're looking for neutrinos. But they don't realize there's 2 different types of neutrinos, apparently, but they show them. This is not from me, this is from Fermilab, I believe. They're showing a muon neutrino, which is the black ball, and they're showing an electron neutrino, which creates the white showers. It's exactly what I showed. No difference whatsoever. Those are the neutrinos. So now where does that leave us? With neutrinos coming through the venturi, and if it's tuned correctly, you get only the white comes through. We can tune this so the white and the black comes through at the same time, and you see the black pushing the white ahead of it. And I already showed you, I believe, the atomic bomb blast, and that other shot will show exactly how that works. Because here, it's all, the white is the only thing that can get through. These must have been really, really tight. Again, it was Rod Warren, not me. Don't give me credit for it. I just want credit for understanding how it works in an electron flood theory. Now, so swoosh, coming through there. All right, so there it is right there. I really want you to understand this. This is the venturi, the two tubes here. It comes through that venturi. And I have shown, another guy did some, Fabien Boulet, and he had red up above and green down below, and it's stunning, the two different, anyway, I'll get into that later. I am certain, because you can actually see totally different frequencies, no question whatsoever. Same particle, different frequencies. So this could also be a source of energy right here when that white stuff comes off. Because when you generate energy, all you're doing is ripping the white part away from the black part and then letting the white part find the black part again, like out here. But it has to go through whatever devices you have to get to that. And it'll burn right through your whole body to get to ground. This is just nothing more than electricity to ground. That's basically what you got there. You could put a harvester right here. I got a little device I drew. You see this? This is it right here. Your laser. The black can't go through. The white squirts through. And it's picked up by an electron collector here. Now you need to use these new transition metal receivers. And they don't have to be out in the cold or in the weather or anything. So the transition metals will pick up virtually all of the energy, and you feed it down through a photodiode, which means they're only one direction. These are photons. Photon, diode, one direction only, and into the batteries. That's all, or into whatever you need to use, and back to ground. You tap off a little bit of it to keep the laser going, which takes almost nothing, because this is like 5 watts, and you should minimum get 1,000 watts. From 5 to 1,000. That's 200 times. And I think it'll be a lot more than that. And then you can run it right through your devices, and you can make this, and put that in a little lunchbox, carry it around with you. It's just, you don't have to be tied to the grid, nothing. This is serious. It's not being taken serious at all. All right. Let's take our time, just 1 minute here, to look at this. Lawrence Livermore, CERN, Fermi Lab, they're all doing the same thing I'm doing. And they're finding these right here, low energy particles, low energy showers. And then what happens out here? They go high energy. Well, what happened? How did they go from low energy to high energy? It created a shower. And they're called electron neutrinos, and these end up being electrons. All right, this is the other side, the muons. They back out. They're too big, can't get through. They bounce back out. So we end up with high energy. High energy. That's what you want. All right, now this is my concept. This is a Geiger counter, but it doesn't matter. As a matter of fact, it's right here. All right, you could take something like this, about the size of this, that's all. And you could put literally thousands and thousands of those amplifiers in there with little tiny lasers, just tiny things. They're all solid state, zillions of them. And every one of them would create its own showers. And then you could have all kinds of different outlets and any phases and all that stuff. And you could walk around with that. You don't have to have that for... You know, what they're talking about is something that you're never going to be able to give to an average citizen. It's going to maybe do the grid, but you could do the grid with that too. Same thing. Only be more reliable, I would think, because anyway, there's a lot to think about here. But I just want to start thinking about it. All right, this goes back to 2016. Light is actually dark matter and light in transit. When it bumps into something, then it turns into completely light, basically. Well, we see it as a complete glow. All right, here's what you have to understand. As light comes through the air, you don't see it. Unless it collides with something, it's just unseen. So I call it dark light. but it's in transit. And this is the theory of how it then turns into light when it concusses, and the fields become entangled, and you get that glow. That goes back to here. This is so. I did a video. I believe it was called "Light is Dark Matter in Transit," something like that, which it is. All right, this is hard for somebody that's not technical to get their mind around. But when you crush these fields together, you come in with a volume like this. Now you got to get it down to a volume that's just a crack here. It forces it to accelerate. It's accelerated just like the nozzle on a hose. The hose kind of dribbles out, but when you put the nozzle on it, you turn it down tight. No difference whatsoever. None. Zero. But you just can't think about it in that terms, most people. But that's what's happening. We sent the light down here. And the only reason, the only, that's my own special word, is only. But the only reason that you can see this exact spot accelerating is because of the venturi. If you had another one over here, you'd get another one because that's another wave here. And if you had another one over here, you get another one because that's another wave. They're all coming down here, but they don't have to accelerate. These are not accelerating. So why, Roger, are they glowing? Because they're being pushed back at. Right? Acceleration is no more than pushing hard through oncoming atmosphere. Being pushed back at makes this push hard through that atmosphere, makes it glow, just like this is glowing. Now, if you know anything about radiation, and you're a techie person, you should fully understand this is what they call reverse EMF. You see it? Why is that there? Why are those waves going this way instead of going this way, which all the other ones are? Even the ones you can't see, they're going this way. You just can't see them because they're not either accelerating or being pushed back until they hit here. Now you can see them. Because this whole thing is just a gigantic subatomic nuclear explosion. Fission and fusion when the black comes back together. That's what it is. It ain't bragging if it's true. It's true. That's what you're looking at there is fission and fusion. And I don't know to be out of focus there, but the particle is coming through here and it's accelerating, pulling itself out of its own wave. It's a magnetic field, and it forces these particles to interact more on the edges, glowing, but then it rips itself right out of that. And at that point, it's going into full photon phase because it really feels like it's impacted with something. That's the only time you get a photon is when you have an impact. You know, the photons, I don't see them. They're all over the place. I don't see them, but I see them bouncing back out of here and hitting off a Caesar and off of the cell phone, and because they're bouncing back. It's basically as simple as that. And every single thing there is, 100%, is coded with the electrons. They will always be on the outside. They will always be on the outside. The dark matter will be inside. That's why you can't see it. It's on everything. That's what gives everything its weight. It's the dark matter. The white stuff has no mass at all. You saw when the atomic bomb went off, the house didn't even move. It just burnt up. All the energy is in this white stuff, which has no mass. All right, I'm going to continue on with Anton here. He's very good. He's a science communicator. He's going to tell you what mainstream is saying about these things, I believe. Let's see what he has to say. I don't think he goes outside the guardrails too much. I'm just the opposite. Here goes.
So many of them out there that naturally they've been also used as a potential explanation for dark matter. Even though their mass is so tiny, because there are so many of them everywhere, they're essentially one of the biggest contenders in terms of explaining dark matter observations. But despite years and years of knowing about them, we basically still know so little about their actual properties, including their mass. And more importantly,
he's now talking about these neutrinos. It's his major discovery about neutrinos. And I can tell you what I think their mass is. I believe it's 1,823 of the black and white particles together in one proton. Just go with that, which is normally considered one atomic mass unit. So all you'd have to do is divide 1823 into one atomic mass unit. I think it comes out to be 0.00058554 or something like that. All right, here he goes. So he's saying they don't know any properties. They don't know what they look like. They don't know how they work. They don't know anything about them. I don't even think they know if they exist.
We still have trouble finding sources of neutrinos, or basically where some of them actually come from. But today it's believed that most of them are very likely the result of radioactive decay. So basically various nuclear reactions inside stars and also inside planets. But also naturally produced by things like supernova, cosmic ray interaction, and maybe even inside pulsars and neutron stars. And so...
All right, so what he's saying, how are they produced? Well, they're produced by crushing their fields together. CERN and all those people, they send these things head on. All right, they did it totally different than us. They sent them head on and hoped they would hit like this and then just break these things into little bits and pieces and see what's inside. And they did every now and then, but like they say, I think they were excited to get 25 collisions out of 100 billion. It was crazy to do what they did for the kind of money they did. And anyway, let's not get too deep into that. What we have to do is to be able to force these particles together, and then they'll just divide like crazy. But they'll come right back together. That's the key. That's the strong nuclear force holding them tight like that. Once they crush so hard that they have to bounce back, the ones that are so tight will go. They won't come back. Hold on a second. I'll show you. Look at this. I'm just scanning over this. Fusion breakthrough. 6 minutes of plasma sets new reactor record. Well, how did they get that plasma? You can melt anything and let it come back together and you have fusion. First of all, you got to break it apart. We did that just with the venturi. How did they break it apart in order to get it to come back together? They have to shoot something, and they think they're blasting it apart, and when it comes back together, they get extra energy. I don't believe that's the case. I think it's the amount of energy they're putting in, and they're going to be able to recover, maybe a little bit more, but I don't think much. All right, this is a tokamak. And a tokamak, what they're doing is they're using big particles. They're using, atoms. And they've got it in this big cylinder, and they're adding a bazillion tons of energy to it, and to make it basically melt the stuff, and then it fuses back together into different materials, and apparently they think it gives off a ton of energy. I don't know about that, but I can tell you what, they had to do this. They collaborated, announced today that the device created a super hot material. You have to add energy to get heat. Or it has to somehow be a process of chemistry. But whatever they did, they created a device, created a super hot material called a plasma. And that's when all of the particles in there have disassociated from being molecules and turned into free-ranging particles. It reached 90 million degrees, and that's Fahrenheit, for 50 million degrees Celsius for 6 straight minutes. So somehow they contained all that energy. Now that's good. You're not going to be able to carry that around with you, first of all. Anyway, the ultimate goal is to sustain a super hot plasma for many hours. But 6 minutes is a new record, and they're just thrilled with this. But I think they had to put as much energy into this to break things apart as to when they saw it come back together, how much energy they could extract. All we had to do is send ours through the venturi. All right, but what they're showing is, for them, collisions do this, and the red ones hang around out here, and the blue ones and the real tight ones, they go and never come back. That's what they're talking about here somewhere. I forget what I guess it's in this neutrino thing. But anyway, I'm showing the neutrinos. I'm showing what they want to see. I just need somebody to engage with. All right, I'm going to tell you what. I'm going to just stop running my mouth and let Anton explain how he has understood the current thinking. Because I'm telling you, I'm 100% out of sync with Anton and all the rest of them too. So it's not that, well, just take it for what you take it for. But here he goes. He's going to be talking about dark matter, and and the neutrinos. This major discovery.
But despite years and years of knowing about them, we basically still know so little about their actual properties, including their mass. And more importantly, we still have trouble finding sources of neutrinos, or basically where some of them actually come from. But today it's believed that most of them are very likely the result of radioactive decay. So basically various nuclear reactions inside stars and also inside planets, but also naturally produced by things like supernova, cosmic ray interaction, and maybe even inside pulsars and neutron stars. And so here on Earth, the majority of neutrinos are believed to be coming from the Sun, specifically from the nuclear reactions inside the Sun, which result in the production of energy, which surprisingly actually gets stuck inside the Sun for up to 1 million years, very slowly making its way out of the Sun. But neutrinos go through everything, so they actually leave right away. And here it's actually important to talk about one of the first experiments and one of the first mysteries in regards to these unusual particles. It's known as the Homestake experiment, named after the Homestake gold mine where all this was performed. Here are the actual pictures from this experiment. And this was conducted in the 60s, only a few years after the original discovery of a neutrino, during a slightly different experiment by Fred Raines and Clyde Cohen that you see right here. The experiment that they actually refer to as Project Poltergeist, because searching for neutrinos was literally like looking for ghosts. And so after months of data collection, they were able to discover 3 neutrino interactions, which eventually resulted in a Nobel Prize something like 40 years later. And so now that we knew neutrinos exist, researchers wanted to find out how many come from the Sun. And they actually made a prediction about how many we should be detecting. But once the experiment was conducted, the numbers detected were different by a factor of 3, which created a bit of a problem. The predictions and the experiment were not agreeing. And so either our Sun was different from what we thought it was, producing a tremendously different amount of nuclear energy, or something was wrong with the experiment. But it actually took something like 30 years to confirm that there was no mistake. Both were technically correct. Because apparently, neutrinos are really strange. Even though right here on Earth we actually expect 65 billion solar neutrinos per second per square centimeters, which is basically why you're getting trillions of neutrinos even watching this video. And by the way, it has nothing to do with the video itself. You're going to be getting them either way, and even if it's nighttime, because they do go through planet Earth without much trouble, the actual number detected is going to be different. And there's a reason for that. Neutrinos by themselves have 3 different flavors or 3 different types. We have the electron neutrino, muon neutrino, and tau neutrino. Which
I have to stop it here because this is where I've come into this significantly. Did you hear the 3 types he's talking about? Let's come back to this. There's 3 types. There's the muon, the electron, and then the tau. The tau neutrinos are just flavors. They're not quite fully formed neutrinos. They're increasing in energy.
By themselves have 3 different flavors or 3 different types. We have the electron neutrino, muon neutrino, and tau neutrino, which basically corresponds to the source of their formation, electrons, muons, or tau particles. Now that's not really important to understand, but what is important to understand is that once they become something, they can change, and they do change at all.
They call it changing flavors. And that's because they're coming through and they're slowing down or hitting other things. So they were this much energy here and they're this much energy here, which would normally be lower. For us, it's just the opposite. Coming into the venturi, there's this much energy here, and then it goes, zoop, takes off. So it gains energy.
All times. Or to rephrase this, neutrinos change their flavors or their types as they travel. And they do this at all times, more so in some conditions than others. And so in 1998, additional experiments started to show that solar and atmospheric neutrinos were changing flavors constantly from electron neutrinos with certain mass produced inside the Sun to other neutrinos such as tau and muon with a very different mass that was not detectable by
All right, there's the key. It's the mass. We're talking about mass. Mass is the value it has on impact. The the photons and the particles, they're not going to change. And you're not only going to detect the mass, first of all, of the muon neutrino. All right, so it's the mass that they're picking up on. And again, these are the particles right here. Now, the faster the thing is going, it has more mass. It's just simple as that. Mass is just like, it's the same particle as the green. You see this here? This is the glowy little edge. And they're both the black here and black here. These are the white ones that get puffy and they get small. And then it's glowing because it's hitting these particles in front of it and they have to push them out of the way. This will get tiny. And this can squirt right through that venturi right there. And that's how you get this completely separated black from the white. 100% separated. That is raw electron energy. And they are muons and electron neutrinos separated into sterile muons and electron showers. There's no missing it. It's not. You don't have to be a genius. And that's exactly what they found at Fermilab. There's the particle with the glowy edge. If it was green, it would be green glowy edge. And show you that? Certainly I can show you that. Now don't forget, you just heard them say they change flavors as they move forward. It's exactly true. These are electron neutrinos back to back, but they're not fully formed yet. Because they only really show up just before they hit something. These only reason you're seeing them is because they're already backing up against their own reverse fields. So out here they're just starting to show up, and then they change another flavor. They tip on this, I don't know, and then they turn into the regular photons. Out here they think it just hit a wall because the backflow is so intense at this spot. Now, once they hit to the venturi, it's all over. They can't get through it. Black bounces back out of the way, and the white continues on. So that is the red. Now don't forget, neutrinos, flavors changing, photon. All right. What about the green? Yes, same thing. There's the green. It's the identical same particle. No question whatsoever, same particle. Zero question. And the other thing is the up and down spin. You see this is going in that direction right here? Why wouldn't it be the particle going sideways this way? It's polarized towards Earth. You understand? Straight up and down. Earth is right down here. Now otherwise it would be twisted like from its trajectory coming out. They're all polarized towards the Earth. Now this one here is just getting ready to flip. You see how this white is all fluffed up? It's going to go, because that's this white here is in the front. This would be considered a down spin. All right, and they see them. They know there's an up spin and down spin, and I think it's the leading edge of, I don't know. Just go with up and down spin. Now, right there though, it's going to flip. And they call that the muon wobble. They know a lot of this stuff, but they just don't pay attention to it. And all of these are traces of particles. This CMOS is just so fabulous, and for some reason, it's this particular phone. You know, I've had some other guys, you know, a couple here and there, but not. Rod was the guy, absolutely, and Fabian Brule did some nice work too. And I didn't. All I wanted to know is, can you make this? Show me what happens. And here's light traveling through the way light travels. It spins. It doesn't flap. It's a spinning particle. So it's just like this. It's really identical to what I'm about to show you. It's like that. When it comes out, it's spinning. See it spin this way and over to that way and spin this way. And there's a whole batch of them. They're everywhere. But the slit is right here. At that point, they're converging and they're just in chaos. And when they come out the other side, they stay away from each other. These do not want to be against each other. They hate each other. All the white ones get split apart. That's what gives you these interference patterns. Those aren't wave flappy patterns doing this and that. Those are get away from me, I'll stay away from you. You get away from me. And they set up these files. You see it? Now listen, think about this. You see this cut right there? Go find yourself a machinist. Ask him what a drill bit face looks like, and that's it right there. Now, right here, I think it's going over and then over here it comes under. I don't know. It's over and under one way or the other, but they're all spinning in the right-hand rule. All right, because there's just something about it. I'm still thinking about this because I found one I think spun off into the left-hand rule and created some really strange stuff. As a matter of fact, I'm going to show you that because this is one of the coolest things I've ever seen. And don't forget, all light turns to the right-hand rule. And if you look it up, if it's going that way, it's spinning this way, right-hand rule. All right, it's going this way, it's spinning this way. That's what they say. Now check this out. All right, these are the exact same fields right here as they see at CERN and Fermilab. Same fields, same big round fields fluffed out like that. Now, what are we actually seeing though? We're seeing the particles. They're seeing debris from a huge collision. That's why they see so many things. We're seeing the exact particles themselves making their own little spins. And here's what happens. These right here. This is the first time I think anybody's ever seen it. Well, I've shown this a few times, but what's going on here is we're looking into the venturi. Now, from here at the venturi out to about here, there's nothing there other than the white. The white is just completely here. There's nothing. You see the little spritzes? They're all coming out here. And then all of a sudden they whack into a black and they turn into the Higgs fields. That's what it is, coming back together. They're not coming apart making the Higgs. They're coming back together. Now, this one right here, that's the key right here. That is something that threw me for the loop. What is that? What do you think it is? I think that is a reverse spinning particle. And what does that mean in terms of energy and concentration of energy and so forth? What it means is a reverse spinning particle, to me, and I could be totally wrong, is dragging its field inside of itself instead of spitting it out as it goes spinning by, or something like that. So it's dragging that field into itself. And I found, I think, where that specific field concussed with another standard field like this. So one of this thing right here, and this is the only time I've ever seen is that one. I believe it hit one of these same type. Now, so here's the one. Don't forget, that little spritz is the spot where there's just nothing but white. And then they whack into something. And here's some other ones over here. This blue and stuff is being pinched. And that was another really interesting shot. All right, check this out. This is over the top outrageous. I am almost certain that is the particle that was the reverse spinner. And it just was turned white. It didn't have a field like that. There was no field. It was just a white particle. Now here it is concussing with this field right here. Now this is a right-hand spinner. This field. It's spinning this way. It's like a record player. This one's a reverse spinner spinning backwards. What happened though was this one spinning this way had enough energy to rip the particle off, because there's only one particle here. There's not, this whole thing isn't saturated with particles, and it ripped that particle right off of the wave as it came by, and they concussed. This one's coming this way, this one's going that way. It grabbed it and ripped it right off, and it's spinning off of there is all I can see. It looks like that to me. All right, you see it? Isn't that something? And then the field just goes away. At that point, it loses its particle. So I believe these fields are a single particle created by the spinning reaction of the light banging back into the dark matter. I don't know. All I can tell you is what I'm seeing. And that's what I see. I'm a material guy. I'm a material guy. I see what I see. All right, so I showed you the light spinning and separating from each other. They hate each other. Stay away from me, I'll stay away from you. I showed you the particle. I showed you the establishment of the little white one. This is just a whole batch coming through. And again, this is the phone, same phone. and is pinched. Some fields came this way and came this way and pinched and actually stepped up the energy. This is only supposed to be red. They don't go higher than that unless somehow you add energy. Well, obviously, you added energy, turned it blue. That's up the spectrum. All right, it came in red and ended up being blue. That's up the spectrum. What did that? All I can tell is pinches, and it's flattened it out almost. And now it's fluffing back up again, and it turns purple in a short distance and then back to red. Very, very interesting work Rod did. Very, very interesting. Here's the red, blue. And again, coming through the venturi over here. Really steaming. The only way you can tell, there's two neutrinos here, back to back, photon, is until you get out here. Back here, it just looks like one. But they're just slowing down enough so you can see it out here. The light speeds up, slows down. It's very silly to think there's any law guiding that whatsoever. What didn't I show you? I think I showed you everything here. And the result was we got down to sterile muons, the black ball, and electron showers, fluffy showers. And they say that's high energy. It creates a lot of energy. And I don't see any reason it shouldn't. And I don't see any reason we shouldn't be able to use something simple like this. Hold on a second. I got another shot. This you could carry around with you. Hold on. All right. Just remember this. I named this Mudfossil University because I discovered the mudfossils, which are these creatures that nobody ever expected. These stones were actually body parts, and I show you. You see that right there? That's an artery of a giant, giant, giant creature, and that right there are the walls of the layers of the arterial walls. And if you look it up, there's like 3, 4, 5 layers, I forget. But they're totally, absolutely, unbelievably distinct. And it's saturated, it's packed with blood. So that's a huge, huge thing for me, is the mud fossils. However, during my course of research, I found out that nobody cares about the truth about this, and they don't care about the truth about anything. So I decided, well, I'll go into everything, and then I had to start the university. I call it Mudfossil University, but it's right across the board. Anything that you can come up with, anything, I will discuss. Now, I want to put one caveat on there. I am a material researcher. I got to show you got to see some material. I can't say, oh, I had this vision, and that's okay. I'm not saying it's going to be wrong. But if you give me nothing to go by, I have nothing to go by. So I am a material guy. These are all, it is what it is. And that right there is a hair follicle from some gigantic creature. That's what a muscle attaches right there. So you can go up on in. And there's where the sebaceous gland is. There's the hair shaft. There's the root ball. And there's the vein and the artery at the bottom. That's material. You can say, oh, it's impossible. Well, no, it's not, because it's here. That's the kind of stuff I hear, that's crazy, that's impossible. Well, no, it isn't, because it's here, it's possible. Now, let's explain it. Let's talk about it. Now, again, some things I'm not going to discuss, I have nothing to say about it. What do you say? But if there's evidence to say, here's why this supports my statements, even some of the ancient texts, I'll look at that as, supporting evidence. I'm not going to say it's conclusive. This is conclusive. There's no more conclusive than that. And all the stuff I have, a lot of stuff I have, DNA tests, I have CAT scans, I have anatomists that have looked at them. Nobody wants to be associated to this stuff because they're scared. They'll be attacked by mainstream. So anyway, let's just set you up for what we're in for.